Okay. Sorry guys if the video was cut short in 16.6. Okay, so that is due to my phone. So, lobat na siya. Okay. So, we'll just continue this in this video and as well as the new topic which is 16.8 later on. Okay. So, moving on with the problem. Okay, so why do we need to study this KSP, or what is this KSP used for? Okay, there can be the condition wherein if we dissolve a solid in a solution, it will give off saturated, unsaturated, or supersaturated solution. And the KSP can be compared with Q, or the ion product, in which we also know this, okay, ion product from the previous chapters. Okay, and if we compare them, so for example, if we have Q, or the ion product, being smaller than the KSP value, so we have an unsaturated solution. Okay, if we have an unsaturated solution, then we have a solution in which we can still put solids, and the solids will be dissolved in the solution. If the Q is equal to KSP, then we have saturated solution. So for the saturated solution, even if we add solids, it will not be dissolved anymore, since in the saturated solution, the solution contains the maximum amount of the solid that can be dissolved in that solution. And in the supersaturated solution, so Q is greater than KSP. So in here, we can, or the solution can have an induced precipitation, or that means initially we have a clear solution, and then after adding a small amount of solid, so the solids, the dissolved solids in the solution will come out as precipitates. Okay, so we will induce the crystallization or the solidification or precipitation of the solids or precipitates. Okay, so let's have a problem regarding this, determining if we have supersaturated, unsaturated, or saturated solution. So exactly 200 ml of 0.0040 molar barium chloride are mixed with exactly 600 ml of 0.0080 molar potassium sulfate will a precipitate form. Okay. So the KSP of the produced precipitate, which is barium sulfate, is given 1.1 times 10 to the negative 13. So in this problem, first you must need to know that we are adding two solutions. So we have 200 ml of this and 600 ml of that. Okay, so that means after adding, we now have a new volume for the solution. That means that this concentration and this concentration will change. Okay, so what you need to do is to solve first the concentration after mixing. How? By using the C1 V1 is equal to C2 V2, or the dilution equation, and then proceed with calculating the Q, or the ion product, and compare it with this KSP. Okay, so again, pause this video and then calculate it. Okay, so we have this solution. Okay, so again, we need first the concentration of the barium and the sulfate ions after mixing, since those ions are required for the precipitation of barium sulfate. So barium ions will come from the barium chloride solution, and the sulfate ions will come from the potassium sulfate ion. Potassium sulfate solution. Okay. So the barium concentration after mixing, so we have 200 ml times the concentration of barium chloride initial divided by the total volume or the final volume after the dilution. So we have 200 ml of barium chloride and 600 ml of potassium sulfate. So if we combine those, so we have a total volume of 800 ml. That is our denominator. So solving, we have 1.0 times 10 to the negative 3 molar. And then for sulfate ion concentration after mixing, we have 600 ml. So that is the initial concentration of, or the initial volume of potassium sulfate times the initial concentration, which is 0.0080 molar, divided by the total volume after dilution, 800 ml. So that is equal to 6.0 times 10 to the negative 3 molar. Okay. So, moving on with the barium sulfate. So, if we dissolve the barium sulfate, it will form barium ions and sulfate ions. So, the KSP is barium ion concentration times the sulfate ion concentration. So, again, the ion product has the same formula with the KEQ, or here we have the KSP, but this time, so again, we have ion product in which the concentrations for this are not the equilibrium concentrations but the initial concentrations. So this initial concentrations is also this barium and sulfate ion concentrations after mixing or immediately after mixing. So plugging in the concentration of barium and sulfate, here we have 6.0 times 10 to the negative 6. The KSP is given on the problem, which is 1.1 times 10 to the negative 13. Comparing this, we have Q bigger than KSP in terms of the value. So therefore, the solution is supersaturated. So again, if we have supersaturated solution, then that means that some of the barium sulfate will precipitate out of the solution. So therefore, we have precipitates. Okay, so from our problems, we always use the molar solubility, okay, which is in terms of moles per liter. But we can also, or I can also give you problems in which it involves solubility, the grams per liter. Okay, so how do we convert the mole per liter to gram per liter? By using the molar mass of the solute, or the molar mass of the solid. Okay, and then vice versa if you need to convert the solubility to molar solubility. Okay, so that was it for 16.6. So we move on, or we skip a topic, 16.7. So we proceed first with 16.8, the common ion effect and solubility. Okay, so again, like any other equilibrium reactions and the ones with the factors that affecting equilibrium, so we have the concentration. So here it's like adding product, okay, in the equilibrium reaction. Okay, so instead of we add a compound in the solution, we just add the ions. Okay, and we call it as common ion effect. So a presence of common ion, or we call that as common ion effect, decreases the solubility of the salt in the solution. So this is again just like the concentration being affected by the equilibrium. Okay, and in the Le Chatelier's principle, if we add a common ion, just like in what we had in the FeSCN2+, okay, So the equilibrium will shift to decrease this added concentration. Okay, so let's have a problem with this. So calculate the molar solubility of silver chloride, molar solubility again, in a 6.5 times 10 to the negative 3 molar silver nitrate solution. The KSP of silver chloride is given. So take note, in this one, we will also use the ice table, but this time we have an initial concentration for the silver ion since we have silver in silver nitrate solution. Okay, so again, please pause this and then try to answer it. Okay, so we have this solution. Okay, so we have silver chloride. Okay, and this solution of silver chloride will give you silver ion and chloride ion. So we perform again the ice table. So on the ice table, we have the initial concentration of silver ions. So that is because silver nitrate solution contains silver ions. And the concentration of silver ions in 0.0065 silver nitrate solution is 0.0065 molar. We do not have initial concentration for chloride ions. So again, in the change in the concentration, we will use S, since S is the molar solubility of the silver chloride solid. So the equilibrium concentration now is 0.0065 plus S for silver ion. For chloride ion, it's just S. And then, getting the KSP expression, or the solubility product constant expression for AgCl, so we have the concentration of Ag plus times the concentration of Cl minus. Okay, so plugging in the values that we know, we have the KSP, which is equal to 1.6 times 10 to the negative 10. So this is equal to the concentration of Ag plus, which is 0.0065 plus S, times the concentration of Cl minus, which is S. And then get the value for the molar solubility, or S. So plugging in the calculator using the solver, or you can do the quadratic equation method, you'll get 2.5 times 10 to the negative 8 molar. Okay, so if you tried to get the molar solubility of silver chloride in just pure water, so this will become 0. Okay, and then compare it with the molar solubility in this solution of silver nitrate, you'll see that this molar solubility for silver chloride in silver nitrate solution is much less than the molar solubility in pure water. Okay, and that is because, again, of common ion effect. So that is the effect of introducing a common ion in the equilibrium, and how does it affect the solubility.